Okay, so if you remember previously, we looked at relations, and a relation could be mapped by a rule, by a set of points, by a diagram. So, and we looked at how we could have a circle, we could have a quadratic. They're all relations, straight line. And so it consisted of a set of points, and those set of points of the set of x values were considered to be the domain of the function, so the relation, and the set of y values was the range of the relation. What we want to do now is look at specific kinds of relations. And one of those specific relations is what we deem, or what we call, a function. Okay? And a function is a relation, has only one unique y value that it maps to, which is jargon talk. So in other words, if I've got a set of points, 1, 2, 2, 3, 3, 4, etc., that would map a function, because that each x value maps onto a different y value. If I add a second point, say 2, 6, all of a sudden that's not a function, because the same x value is there. Okay, so they've got to be different x values mapping onto different points. Graphically, it's much easier to see, and we might have a look at that. Okay, so sketch the graphs on the following relation, state the domain and range, which we've been doing a bit, and state whether it's a relation or a function. So y equals x squared, so I might just use the red pen, and we'll assume that's the point 1, 1. And since we should get in the habit, x is equal to 1, y is equal to 1. The domain, we could see no restrictions. The domain, the set of the x values, is equal to r, and the range is, well, the lowest value is 0. And we'll just go from 0 to infinity. Okay. Now, the easiest way to tell if a relation is a function is if we sketch a vertical line anywhere on that graph, as long as it only crosses once, it's a function. Okay? So I can say that it is a function. Okay, so let's have a look at the set of these points here. If we let's go with the -6, -4, whoops, undo that. We'll go -2, -4, 2, 4, pretend it gets up to 4, 2, 4, negative. We may not get them all in, but we'll get an idea. The point -2, 1 might be there. The point -1, -1, -1, -1. Oh, sorry, concentrate, Mr. Gar. -1, -1. The point 0, 2 is up there. The point -2, 1. So -2, 1 is identical, so we've got 2 there. And the point 2, 6, 2, 6 is up there. Okay, so even though, so there's our 4 points. So let's go through and let's have a look at the domain. Is all the x values, so it's specific values this time, -2, -1, 0, and 2. I don't repeat. The range, I'll use my colour scheme. The range is, try and go in order, -1, 1, 2, and 6. Is that right? 1, 2, 3, 2 1s there. Yep. Okay, so there's our domain and range. And is it a function? Well, if I draw a vertical line through that point there, I go through 2 points in my graph, or 2 points in my relation. So no, it's not. Since I've repeated a point, it's not a function because it has to be unique. All right, x squared plus y squared equal to 4. Hopefully we remember it's a circle with a radius of 2. So they're going to be my I'll just draw that circle. It's not too bad. -2 to 2, -2 to 2. My range, the y values, -2 to 2 square bracket. My domain, the x values, domain, also -2 to 2. Is it a function or not? I'll swap the colours. No, it's not, because I can draw a line in a couple of different places and go through 2 different points. So, no function. What's the last one? It says -1, the point -1, and y can be anything. So, to give us a sample of the points there, so I could have the point -1, 2, -1, 3, -1, 4, etc., etc., etc. So if I call that -1, well then those sets of points are all along those lines there, because y is any value we want. So the domain, get the colours. So my domain, well, what x values can I have? It's just equal to -1. The range, well, I can have any y values I want. R. Is it a function? Well, no, it's not, because obviously I can draw a vertical line through that point there at x equal to -1 and cross it infinitely many times, so not a function. So really this little exercise here is just giving you a visual idea of what is a function and what's not a function. Okay, so visually, if I can do a vertical line and it crosses the relation in more than one place, it's not a function. Let's get more formally now and talk about our function notation. If a relation happens to be a function, well then there's a few different things we happen. Notation changes. Okay, so we tend to use the letters f, g and h to represent a function, f of x, g of x. And you've seen that notation on our CAS calculators. Okay, so the definition of a function tells us that for each x in the domain, there is a unique y. By definition, if it's a function, that's the case. Okay, now a fully written function is defined as that. Okay, that's my function notation. So what that says is for a function, I guess in English we could say for function f such that the domain elements x, we use a terminology map onto y, which is the codomain, for the rule f of x equal x squared 2x, x minus 3x plus 6 or whatever, you know, all right? So the only other definition there, and it's written down here, is that second point there is what we call our codomain. Well, there's a few significant things in here. That point there is definitely our domain. So whatever that value, if it's an R, or if it's from -1 to 10 or whatever it is, that's the domain of the function. The y are the set of values that our function map onto. So it doesn't tell you which ones, it just means it maps onto that. So typically we have R as my codomain, especially for us in our methods course. So what we're saying is that our function, all the y values will be a part of the real number system. Which values they are, we're not too sure about. We have to work that out, but they will be a part of the real number system. All right? So let's have a look at this example 2. Let's rub out that highlight there, makes it a bit messy. Rewrite the following using the XR notation. So what's this telling me here? This is telling me I've got a function f of x, there's the rule, and the x values are an element of 1 to 5. So what my formal notation is I've got a function f such that the domain, which is 1 to 5, maps onto all the real numbers such that f of x equals x plus 2. All right, so that's the same notation as up there. Earlier in our earlier examples, we might have written this information as a set of numbers x, y such that y equals x plus 2. That was the notation. That's a bad curly bracket, isn't it? Not much better, but that's the notation we used earlier when we were just talking about relations, the graphs that we had to draw in our gallery of graphs. So that was our typical notation. So what this notation tells me, this f of x notation, say x squared plus 3, is wherever I see whatever's in this bracket here goes into there. So if I would decide to work out f of t, that would be t squared plus 3. F of 1, if I put a value in, I substitute the 1 in. 1 squared plus 3. So over here in our examples, I've got a rule for f of x. If I want to work out f of 2, I substitute, I might try color code a little bit here. Wherever I see an x, I put in a 2. And if I just keep, I'll go down, is equal 2 times 2, which is 4, minus 2 squared, which is 4, which is equal to 0. So f of 2 is equal to 0. F of negative 1 is equal to 2 times, wherever I see an x this time I'm going to put negative 1, minus negative 1 squared, which is equal to 2 times negative 1 is negative 2, minus negative 1 squared is positive 1, minus 1, which is negative 3. F of t minus 1 is equal to 2 times x, but x in this case is t minus 1, minus x squared, which in this case is t minus 1 squared. So now we just have to be a little bit careful with our algebra and expanding. So I get 2t minus 2 minus, in bracket, what's t minus 1 squared? It's t squared minus 2t plus 1. Yeah, it's not just t squared minus 1 or t squared plus 1. So let's expand all that as well. 2t minus 2, negative sign multiplies through everywhere. That a bit clearer. So I've got two lots of 2. So I've got a negative t squared. 2t plus 2t is plus 4t. And minus 2 minus 1 is minus 3. So that's what we expand to. Finally, f of t, well, it's just a case of replacing x with t, so that's just 2t minus t squared. Okay, so my function notation, it's just another way of substituting in. Okay, it's an easier way to saying, you know, we could have, so if I just give you one more, if I've got f of x equals 2x minus x squared, and I put in f of 2, well, we just decided that was 2 times 2 minus 2 squared, yeah? Well, that's the equivalent of saying y is equal to 2x minus x squared at x equal to 2, y equals. And now we substitute x equal to 2 in. So it's just a nicer, cleaner way of putting in that information. Let's have a look at B. For what value of t is f of t equal to t? So what was f of t? So f of t equal to t means, what's f of t? 2t minus t squared has to equal the right hand side, which is t. So let's make it a bit, sorry, what that one, just so we're a bit clearer. F of t is equal to t, and so that's that t there. So now how do we solve this equation? We group all the terms together, get like terms. So let's bring that. So if I subtract, so I've got 2t minus t squared. I'm going to subtract t now, equal to 0. So what does that mean? 2t minus t is t, minus t squared is equal to 0. So how do I solve a quadratic? I try to factorise. So I'll take a t out the front as a common factor, and I get 1 minus t is equal to 0. Therefore I get t equal to 0, or 1 minus t is equal to 0, so 1 is equal to t. So therefore t is equal to 0 or 1. Okay, so I could check that. If I put 1 into my equation, I get 2 minus 1, which is 1, which is the answer. If I put 0 into the equation, I get 0 minus 0, which also equals 0. So that's fine. Now, for what values of f of x, is f of x greater than or equal to x? So similar. All that's really changed is the pronumeral that we've used. So we're going to use an x again. So f of x is greater than or equal to x. What's f of x? F of x is equal to 2x minus x squared. Has got to be greater than or equal to the right hand side, which is x. So you can hopefully see the math is exactly the same. So I've got x minus x squared is greater than or equal to 0. So if we remember from our quadratics, I always thought the easiest way to solve these, we'll factorise the next line, x outside of 1 minus x equal to 0. So if I had to sketch this graph, I'd have a graph there, intercept there at 0, another one there at 1. And it's a negative quadratic, so it would go up and down like that. So I'm interested in where is this greater than or equal to 0. So if I just highlight the section I'm interested in between 0 and 1. Therefore, 0 is less than or equal to, because it was a less than or equal to sign, less than or equal to x, which is less than or equal to 1. So in other words, if I pick a number between 0 and 1, the left-hand side will be greater than the right-hand side. F of x will be greater than x. Okay, so we've solved these before. That same question in the past would have just been solve y equal to x, y equal to 2x minus x squared, solve point of intersection maybe, we might have written. Yeah. It's a, all right, a little bit more about our functions. Okay, there's quite a bit in this little exercise. So we've got those 3 graphs there, or 3 functions that all represent a parabola, and they're all slightly different. And because, well, I guess the key is what's making them slightly different. And the difference is, look at the domains that each one has been defined for. Yeah. So even though they're the same rule, f of x equals x squared, because they have different domains, they're actually different functions. All right. So each of those functions or rules are defined only for the domains that are given. All right. So the functions G and H are very similar to F. They're just restrictions. It's the function F, but with some restrictions on the domain. And that's what we call them. We call G and H restrictions in F, since their domains are subsets of the original function. So let's have a look at each of these graphs. And again, pay particular attention to the domains that we've been asked to sketch it over. All right. So I get to cheat a fraction here because the rule is f of x equal to x. So I can just do a reasonably straight line. That's the full function, except our function is between -1 and 2, which means there's my domain there in the blue line. So I've got to restrict my function. It only goes as far as when x is 2, and it only goes as far as -1. So there's the point -1 something, there's the point 2 something. So since y is equal to x, that's the point 2, 2. That's the point -1, -1. So they're the coordinates. The only thing I now need to consider is that end bracket. What sort of dots do I put on my graph? So you're always going to have to decide that. If we restrict a function, you're always going to have to decide, well, what are my endpoints of my graph? Well, at x equal to 2, it's a square bracket, so it's a... Oh, I don't want to use that one. It's a solid dot. But at x equal to -1, it's a round bracket, so it's not included. So it's a round dot or a hollow dot. Okay, so there's my restricted function. State its range. Well, the range is from up there at +2 down to there at -1. So for this particular graph, the range, lowest number goes first, which is -1. Bigger number goes second, which is +2, and they've got to make sure we've got the brackets right. All right, quick sketch, x squared plus 2x. x plus 2 if I do a quick factorise, which means intercept at 0, intercept at -2, turning point halfway between. So if I even just work out what f of -1 is, I get -1 squared plus 2 times -1, 1 minus 2, which is -1. So it's at the point 1, -1. So if I do the whole graph, it looks like this. But now I've got to consider the restrictions. So it's from -1 to 1. So what does that mean? So I'm going to highlight my domain again. -1, everything's a square bracket. So it's just this section of the graph that I want to draw, because that's my domain. I've got my eraser, so I'm going to rub out this section because I don't need it. And I'll just tidy that up a little bit. I'll tidy that up, but we want that. I'm going to cheat up to there, say solid dot, solid dot. So again, I need to work out coordinates. So at -1, I did talk about that. It was going to be the point -1, -1. The point up here at x equal to +1, 1 plus 2 is 3. So my graph's a little bit out, isn't it? Probably should be a bit steeper. If that's 1, yeah, it's probably not steep enough. But that's okay. So there's my graph. Let's check. Oh, it's a hollow dot at the right-hand side. Good thing I checked that. Hollow dot at the right-hand side because it's a round bracket. All right, and so again, let's consider my range. So the range, lowest number is -1, and we're including that value. The highest number will be up here at 3, but 3 is not inclusive, so we put a round bracket. All right. All right, hopefully all this graph sketching is still strong in our minds. All right, we've got the graph of 1 on x squared, so hopefully remember. I probably should use a ruler for my asymptotes. We should always use rulers. So I've got a horizontal asymptote. I probably shouldn't have used that colour. That's my domain or range colour. At x equal to 0, a vertical asymptote on the y-axis. Yep. So remember we label them x equal to 0, y equal to 0. We know it's x squared, so all parts of the graph are going to be positive. And if I just, we should get in the habit of labeling a point. So I'm going to have it come up like that, and like down like that. And if x is equal to 1, if I substitute 1 into the rule, I get the point 1, 1. So it gives us an idea of the dilation. Negative 1. I'm going to say I'm pretty happy with the graphs, the way they've come out, boys. Not so good, that one. If I put negative 1 in there, I also get the point 1. So we just label a couple of points so we get an idea of dilation. Now, there's my full graph. So we only want to sketch the graph between negative 1 and 3, excluding 0. Well, we can't have 0 because it's an asymptote. So let's get, I'll use red, between negative 1 and 3. Negative 1 is around, so hollow dot all the way across to wherever I think 3 would be, which might be over here somewhere. Okay, so that's the domain of the graph that I want to sketch. So again, let's rub out the bits that I don't want. I might just tidy this up a fraction. And try and get it to, oh, get rid of that. And we'll call that 3 there. Okay, so it's those two sections between 0 and 3, or sorry, negative 1 and 3, I should say. That's a highlighted dot. So we've got negative 1, positive 3, solid dot there, which means I'm going to put a solid dot on the end of my graph and an open dot on that end of my graph. Before we consider the range of the function, I guess we've got to really finish off this coordinate here. So I do know that the x coordinate is 3. If I put x equal to 3 into 1 on x squared, I get the point 3, 1/9. That becomes significant, doesn't it? Because if I now map out my range of values, 3 is inclusive, so I've got a solid dot there, and it's going to go all the way up from there. Okay, so the range of this graph is going to be determined by the right hand side, because the lower limit at x equal to 3 is included. Oh, at x equal to 3, which means I have a corresponding y value of 1/9, and it continues up indefinitely. Okay, so we just, again, whenever we have a domain restriction and you've got to look at your range, always plot your graphs, identify your endpoints, and then just have a look at it. Finally, we've got x squared minus 2x plus 8. Since we're talking domain and ranges, it really is important that we have our turning point. So if I complete the square, halve it, negative 1 squared is positive 1, minus 1 plus 8. There's my perfect squared, so x minus 1 all squared plus 7. So that's the completed square form of it. I could also use minus b, so it gives me a turning point of 1, 7. I could use minus b on 2a to give me a quick idea, which gives me a positive 2 over 2, which is also 1. So the point 1, 7, well, I'm going to call that 1. I might just call that 7 there. It's a positive parabola. If that's 7, 1, 2, 3, 4, 5, 6, 7 would be there, I should say. That would be 8, which is the intercept. So, oh, I missed it. Let's undo that. So I'm going to go maybe something like that, and I'll make it just as sweepingly wide, so it's got a bit of symmetry about it. And that's the 0.17, the 0.08. Clearly there's no intercept, so I don't have to worry about that. And the domain in this case is R. So I'm sketching it for everything. So if I concentrate on the domain of the graph, my x values can be everything, which means the range of my graph is from here all the way up. Yeah, so I'm going to put the range in as the lowest value was at 7 inclusive up to positive infinity, and I don't have to state the domain. All right, so I hope that gives you a little bit to think about. Key points: the domain always will define our range of our graph. All right, a function is only a function if for every one x value there's only one y value. We can have different x values give us the same y value. So you look at the quadratic here that we've just finished drawing. Obviously that point there at 8, 0, 8, is the same as that point there at 2, 8. So two different x values can give me the same y value, but I can't have the same x value in there. All right, off we go. Terminology we used. Restriction.